Well, hopefully the rest of the class gets here shortly. We called everyone. That's about all I can do. So we're going to get started. We've got an activity today for going over the concepts from yesterday, section 11.2. We're going to do with inference on two-way tables, or two new chi-square tests. And so for this, I do have a Desmos activity, which I will drop the link for into the chat here, so you can get to that. All right, so that link should be there now, and you can join the activity, or you can just go to student.desmos.com and find the AP Stats 11.2 activity inference for two-way tables, and you can get to the same place. All right, you will be restricted to the first screen. It's not a check-in screen today, it's just the first screen of the activity, which is, again, we'll do some review before getting into the questions that we will answer. We'll take it from there. This activity might take a little bit longer than normal, but we just kind of got to get through it. So I apologize in advance for the length of this. All right. So here we go. Our first screen here is just the introduction to section 11.2. All right, we can use a two-way table to summarize data involving two categorical variables. To analyze the data, we compare the conditional distributions of one variable for each value of the other variable. Then we turn to formal inference. Two different ways of producing data for two-way tables lead to two different types of chi-square tests. All right, first we have our chi-square test for homogeneity. This is when a study aims to compare the distribution of a single categorical variable for each of several populations or treatments. In such cases, the researchers should take independent random samples from the population of interest or use the groups in a randomized experiment. The null hypothesis is that there is no difference in the distribution of the categorical variable for each of the populations or treatments. The alternative is that there is a difference. Right, the chi-square test for independence. This is when a study is designed to investigate the relationship between two categorical variables. We're looking for association. In such cases, researchers take a random sample from the population of interest and classify each individual based on the two categorical variables. The null hypothesis is that there is no association between the two categorical variables. The alternative is that there is an association. Another way to state the null hypothesis is that the two categorical variables are independent in the population of interest. And so this is the idea of this section, being able to do both of these types of tests, decide which one is correct, and then be able to do all the proper calculations and testing. It says we do for any inference method, we have conditions that we must do. All right, conditions for performing a chi-square test for homogeneity. Why is the other one missing? Something happened. Something went wrong here. I'm supposed to have two pictures in there. There it is. It was lagging. Yep. All right, there we go. We got both conditions here now. So we have conditions for performing a chi-square test for homogeneity. When we're doing the test for homogeneity, the random condition is that the data come from independent random samples or from the group in a randomized experiment, from the groups in a randomized experiment. Okay, independent random samples, that's important. Meaning we're not sampling from the same populations or same groups. All right, we have the 10% condition when sampling without replacement, and our large counts that all expected counts are at least 5. For the chi-square test for independence, our random condition is that the data come from a well-designed random sample. And typically when we're testing for independence, we're sampling from a single population or randomized experiment. 10% condition when sampling without replacement, and the large counts again is the same, that all expected counts are at least 5. These conditions must be checked when you're performing an inference. The way we find expected counts is the same whether we're doing a chi-square test for homogeneity or for independence. We use the same method. Right, when the null hypothesis is true, which is the assumption when we're finding expected counts, the expected count in any cell of a two-way table is the row total times the column total divided by the table total. We will be using this soon. Here we have the basic rundown for how to perform a chi-square test for homogeneity. Right, there's some sample hypotheses just in general without a specific context. You can use those as kind of templates if you need. So we suppose the conditions are met. We use the chi-square test for homogeneity to test our two hypotheses. Right, we start by finding the expected counts, calculate the chi-square statistic, and then use that chi-square statistic to find the p-value based on degrees of freedom, which are the number of rows minus 1 times the number of columns minus 1. Right, and that p-value is the area to the right of chi-squared under the corresponding chi-square density curve. Similarly, we have the rundown for the chi-square test for independence. We do have two different samples of how to write the hypotheses there. You can write the hypotheses as the null hypothesis, as there is no association between two categorical variables in the population of interest, versus the alternative that there is an association between the two categorical variables in the population of interest, or you can write it in terms of independence, where the null hypothesis of two categorical variables are independent in the population of interest, versus the alternative that the two categorical variables are not independent. Remember, independent means that knowing one thing influences the next thing or influences another thing. If they're independent, that means they have no influence over each other. And then similarly to the other test for homogeneity, we have to find our expected counts, calculate the chi-square statistic, find the p-value based on the given degrees of freedom, and then we can make a conclusion and interpret that p-value. So these are here for your reference. Next, we have a short video here showing you a way to do a chi-square test on a two-way table on the calculator. This will use a method using matrices in your TI-84 calculator. While this method might seem a little bit time-consuming, it takes less time than doing all the individual calculations to find the chi-square statistic. Okay, so we'll do this, which go there, and I think. Can those of you at home hear the video? Someone give me a thumbs up or something. Sweet. All right, cool.
Other parts of statistics. In this example, we're interested in seeing if there's no difference in the true distribution of his word or time students existing in place. To begin, we'll enter our data in matrix A. Hit second, X-1, go over to edit, and choose edit matrix A. We don't want matrix A to be a 1 by 1 matrix. We want it to be a 3 by 3 matrix. So hit 3, enter, 3.
All right, excellent. So hopefully that was somewhat informative on how to use the calculator and putting in our tables and things that we'll be using. When you're entering in a matrix in your calculator, the first number for the size of the matrix is the number of rows. The second number is the number of columns. Right, so if you have like, depending on the number of rows and columns, it will show you on the calculator how many rows and columns there are. So you should be able to see if you've entered in the X by Y matrix properly, but first number is the number of rows, second number is the number of columns. I don't know that there's any benefit to drawing the distribution here. Since we're taking the digital exam, you will not be expected to draw a distribution. So you could draw on your, have it show up on your calculator, but I don't know the use of that at this point. It's more important to be able to find the chi-square statistic and the p-value so you can then use those to make conclusions. Right, is there anything I can clarify about the calculator? So that brings us to the first question. All right, there's a big old context there. Has modern technology changed the distribution of birthdays with more babies being delivered by planned C-section? Miss McDonald's statistics class hypothesized that the day of the week distribution for births would be different for people born after 1983 compared to people born before 1980. After all, why would a doctor plan a C-section for the weekend? To investigate, they selected a random sample of people from each of the two age categories and recorded the day of the week on which they were born. The results are shown in the table to the right. Is there convincing evidence that the distribution of birthdays has changed? So first, we're going to calculate the expected counts for the two age groups, assuming that there is no difference in the distribution of birthdays. So assuming the null hypothesis is true. Similar to the table we saw in Desmos last week, you can put your answers right in here and it will tell you whether or not they are correct. You also have access to a calculator at the top of your screen to help you do these calculations if you need to. Recall, so to find this first entry here, for example, we need to take the row total times column total divided by table total. We can type it in just like this in the calculator, just the way that it shows up. Right, because multiplication and division are the only two operations going on, right? This works out just fine this way. We don't need parentheses or anything. So then, for example, the first expected value for before 1980 and on Sunday is 10.78. And you can do a similar type of calculation for the next one, which would be 21 times 73 divided by 150. Everything on this table will be divided by 150, because that is the table total. All right. If you get the two values for a row correct, it will show you that it is correct. Otherwise, it's incorrect. Please round to 2 decimal places. Please. Just going to make it so you can actually see your answer and everything. All right. Take a few minutes, fill out this table, and we will talk about it shortly. Alrighty, it looks like we are on our way for most of us on filling in this table. Some of you have completed the table. Some of you are just partially way through there, and that is okay. The idea is that you're doing the process correctly. So even if you haven't completed all the rows of this table yet, that's fine. All right. As long as you figured out how to get some of them correct so far. All right. Now, finding your expected values with tables is somewhat easier because it keeps things pretty well organized. Right? The expected value for after 1993 and Sunday uses the entry from this table. We're looking at this row and this column. All right, so we'll do 21 times 73 divided by 150. So we can go back into here and just switch that to 73, and we get our next value, 10.22. Monday before 1980 for this table, we'll use this row, 23 times 77 divided by 150. We get 11.81 after rounding. And we'll just go back in, same row, so 23 stays, times 73 divided by 150. Get 11.19. And we can continue to fill in each cell in the table that way. It's important to stay organized when you're finding your expected values. Okay, so having a table can be very helpful. Is there any questions about how to fill in the expected counts? So next, where'd it go? There it is. We want to find the chi-square statistic. Please use the values on the two tables provided. I do know that there is some discrepancy between the expected counts that the book found and the expected counts that we actually calculated. Not sure why that is, but there is a slight difference. So please use these values to find your chi-square, because that's what was used to find what the chi-square statistic is as far as marking this right or wrong. All right. So the tables pictured to the right show the observed, which is the first table, count observed and expected counts, second table. For the birthday study, calculate the chi-square statistic. Please only type in the number and round to 2 decimal places. I do not need you to type in the whole like things that you're adding up and multiplying, dividing, all that stuff. I don't need you to show the variable. I just want the value of the chi-square statistic. All right. Now, this would be an excellent opportunity to practice using your calculator to find this. because calculating all 14 of these and adding them up will take time. Right? It's not the most efficient way. So I do suggest if you have your graphing calculator to use your graphing calculator to do this. Right? And try the matrix. Okay, I can show you quickly again how to set that up if you want. Right, you'll go to second, x minus 1. Right, we have a 7 by 2 matrix here. I already set it up in the previous class. Go to edit. Right, you'll click over twice, go to edit, and that'll allow you to enter in all your values. Matrix A should be your observed. So it's everything from this top table. It needs to be a 7 by 2 matrix, and fill it in exactly the way it looks. 12, 9, 12, 11, 14, 11. It should match the order in which that table is set up. Okay. You go back into your matrix, go to edit again and edit B. Another 7 by 2, except now you're going to use the values from the expected counts. I don't know why those values have changed from what I typed in, but they're different now. I don't know. Something happened in the calculator. Either way, that should be okay. So again, these values will just be the same as what we had on here. And we get 11.78. Is actually, okay. Yeah, it looks like the calculator actually did something between the observed counts and the chi-square statistic and all that stuff that it actually calculated previously and adjusted these values. Because these values match what the textbook had before rounding. So I'm not sure how the calculator did that. I have no literature on why the calculator did that, but it did. Either way, don't mind that. Type in these things, you'll get the right values. All right. So we'll give you all a couple minutes here. If you do not have a graphing calculator, you're gonna have to do this by hand. I apologize. Alrighty, so the chi-square statistic for this scenario here, based on the observed and expected counts, should be 6.55. Right. And that's if we round it to 2 decimal places. Obviously, we get a much longer decimal than that when we calculate it. Right. But this is what we want. All right. Does anyone want to see how this is done with the calculator? Please raise your hand. All right. So, there it is. On the calculator here, I've already input everything we need in the 2 matrices. Right. So I don't need to edit the matrices at this point. I just need to use them. So we will go to stat. We'll go over to tests. We'll do the chi-square test. Our observed is matrix A, expected is matrix B. It's already in there that way. Your calculator will default to use A and B unless you've put something else in there in the past. All right, so it should just be set up to A and B already. All right, we'll go to calculate and enter. And there we go. So we get chi-squared is equal to 6.549113254, and it probably goes longer than that, but that's all the calculator will show. So we round that to 6.55. We actually also get a p-value from this calculation of 0.3645, which would round it to 0.3646 or 0.365, depending on how you round it. Right, and we have 6 for the degrees of freedom. That makes sense because we have 7 rows, 7 minus 1 is 6, and 2 columns, 2 minus 1 is 1, 6 times 1 is 6. Okay. So this gives us a lot of good information that we can use, right? We're going to need the p-value, right? If you use this method on an AP exam or on one of my free response questions, you need to say that that's what you used. Say that you use the calculator, you put your observed and expected counts into matrices and use the chi-square test function, right, to calculate the chi-square statistic, the p-value, and we had degrees of freedom of something. Give that detail to the person reading your responses so that they know that that's the method you used. If you just give a chi-square statistic and don't show any methodology to how you got it, you will not get credit. You need to have something showing how you did it. Okay. Anything I can clarify about the calculator example here? So next, the hypotheses for the birthday study are: there is no difference in the distributions of birthdays for people born before 1980 and people born after 1993. Versus the alternative, there is a difference in the distributions of birthdays for people born before 1980 and people born after 1993. The value of chi-squared was 6.55. That's what we just found. We're going to assume that all conditions have been satisfied. We're going to use table C. I made that a link. To find the p-value. Then use chi-squared CDF command on your calculator. You could also choose to use what we just did. Right, use the entry box below for the p-value from table C. I swear I made that a link. Is that a link? No. Did I put that on the wrong thing? Sorry, it's linked here. Sorry, table C should be a link there, but I don't know if it is. It's showing up as a link here, but not on this. Don't know why. So anyway, the table C down here should be a link. Otherwise, there is a link to the formulas and tables actually in Teams. If you go to the files in this class in Teams, it should be there, and it's also in Canvas. Right, so please answer what the p-value is, and we'll talk about it shortly. So first, if we look at the entry box, I put in there p-value is greater than. There's a one-sided inequality here. A lot of the p-value inequalities we've seen have been two-sided, showing that it's greater than some value but less than another value. That's somewhat typical when we use table B or table C. In this case, this is a one-sided inequality. We just get to know that the p-value is greater than a certain amount. I'm going to show you why. So if we look at table C here, and we're looking at degrees of freedom 6. Right? Every value here is greater than 6.55 as we move to the right along the table here. That means that 6.55 is somewhere here to the left of 7.84. Anything to the left of 7.84 has a probability greater than 0.25. It just goes off the table to the left there. So all we can say is that we know for certain that the p-value is greater than 0.25. We could have similar outcomes on the other side of the table. Right? If we get to some value greater than 24.1, we would then have a p-value that is known to be less than 0.0005. We can't say that it's definitely greater than something. We can only say that it's less than that p-value. Okay, so in this case, we can go off the table. It's just we end up with a one-sided inequality. Which then means, my mouse, there it is. And in this case, we can only say that the p-value must be greater than 0.25. And then we saw a p-value previously on our calculator. We can use the chi-square CDF function as well to get a different, slightly different value. So I'll show you that. So this is what we got using the chi-square test. We got the chi-square statistic, p-value in degrees of freedom 6. And this one we get 0.3646 would be what we round this to if we're doing 4 decimal places. We can also use, if we go to second vars, above that says distribution, and we'll go down to the chi-squared CDF. This one right here. All right, for the lower, we'll put 6.55. Right, upper, we'll just put a big number. 1,000 is fine. There's no upper bound on this. It's just greater than that certain chi-square value. Degrees of freedom is 6. We'll hit paste and we'll hit enter again. We get a slightly different p-value using this method. We get 0.3645 rounding to 4 decimal places. Right? The difference between the two is not significant enough that we should use one instead of the other in this case, or in most cases, right? Because of what the p-value is, we know that it's definitely greater than whatever alpha we have already. So it's not going to change our ultimate results or the conclusion. So you can use either method, but again, make sure to tell the grader what method you use to find the p-value. Don't just say the p-value is something without showing any way that you calculated it. You've got to show something. Okay. And so we can put 0.3645, right? Get that and that. Is there anything I can clarify on this part? Any questions? All right, let's move to the next one. All right, so now, using this is also the same context. P-value from the birthdays study was 0.3645. We're just going to go with that one. We want to interpret this p-value from the calculator in context. Then we want to write what conclusion you would draw based on that p-value. Please justify your answer. Okay. Now note that these are two separate things. The interpretation is telling me, what does this probability, what does this p-value represent in context? What is it saying? The conclusion says, okay, based on this p-value, do I reject the null hypothesis or do I fail to reject the null hypothesis? Right, so let's take a few minutes to write up these statements and then we shall talk about it. All right, here we go. Let's do these. All right, so again, when we interpret the p-value from our calculator, we are trying to say what this means in the context, right? Our p-value is always calculated based on the assumption that the null hypothesis is correct. And that's what all p-values are calculated on, saying that our null hypothesis is correct. So we're going to find the probability of this certain thing happening if this is the proper distribution. Right, so this is one possible way to interpret this. Assuming that the distribution of birthdays is the same, which was the null hypothesis, the distribution is the same. There's about a 0.3645 probability of observing a difference in the two distributions of birthdays among the two age groups as large or larger than the one in this study. That's what the p-value means. So remember that p-value is based on our chi-square distribution, and the p-value says the proportion under the curve greater than a given chi-squared statistic. So it's the probability of having that value or larger, assuming the null hypothesis is true. And in general, when we're interpreting a p-value in context, that's what it's saying. Assuming our null hypothesis is true, there is some probability of observing a difference, or whatever your test is about, in our distributions or whatever, that larger or larger. That's what the interpretation is. You should not be saying anything about a significance level in the interpretation or making an actual conclusion about what we have evidence for. We're just saying, what's this probability represent? Now in the conclusion, that's when we say, okay, well, based on this p-value, should we have seen the results we saw if the null hypothesis is correct? It's basically what our significance level allows us to do. If no significance level is provided, we automatically default to using alpha equaling 0.05. Right? If our p-value is greater than alpha, we fail to reject the null hypothesis, which means we do not have evidence for the alternative. If the p-value is smaller than alpha, then we reject the null hypothesis and we do have evidence for the alternative. The p-value kind of represents the probability of seeing what we saw if the null hypothesis is true. If the probability of that thing happening is high, then there's no reason to reject the null hypothesis. The null hypothesis could be true. Let me fix that guy. Right. In this case, because the p-value is large, 0.3645 is greater than alpha, we fail to reject the null hypothesis. We do not have convincing evidence that there is a difference in the distributions of birthdays for the people born before 1980 and the people born after 1983. Essentially, we could have seen this result just by chance. It's totally within the realm of possibility, so we don't have enough evidence to reject the null hypothesis. Is there anything I can clarify about the difference between these two statements? Get to this last little bit here. Again, I apologize for the length of this, but this is the stuff we've got to get through. Where'd my mouse go? There it is. All right, so this is just an information screen here. Which chi-square test to use? To help recognize which test to use for a given context, you should think about how the data were collected. Take note of the number of populations or groups and the number of variables. Here's a quick summary. For the goodness of fit test, which was from section 11.1, we have one variable in one population, which is why we end up with a one-way table. For the test of homogeneity, we have one variable in two or more populations or groups. Right? The homogeneity test involves randomly sampling from two separate groups or populations. Right? And then we're testing one variable. For independence, we have two variables within one population, meaning we take a random sample from a population we're interested in, and then collect data about two separate variables, like being male or female and having a preference about something, I don't know, right? Categorizing after collecting our sample. Right? Homogeneity is separating the two groups, randomly sampling, and then checking about some category. Right? So I'm going to use that to answer these multiple choice questions. We have 3 context below, carefully read the 3 given contexts below and select the appropriate chi-square test that should be used. You do not need to perform any calculations or actually perform the significance test. Please just choose the appropriate test. All right. So read them carefully and try to decide how the data was collected. Right, refer back to that previous page. Right, give you all a few minutes and then we will talk. All right, so let's talk about these guys here. So in our first context, right, is there a relationship between attendance at religious services and alcohol consumption? A random sample of 1,000 adults was asked whether they regularly attend religious services and whether they drink alcohol daily. So we have a single population of interest and 2 variables. This is a test for independence. They're checking for a relationship, which could also be called an association. Right, so we're trying to see if one has an effect on the other. The next one, Canada has universal health care. The US does not, but often offers more elaborate treatment to patients with access. How do the 2 systems compare in treating heart attacks? Researchers compared random samples of US and Canadian heart attack patients. One key outcome was the patient's own assessment of their quality of life relative to what it had been before the heart attack. So we have 2 separate populations, US and Canada, and 1 variable. Right, the 1 variable is their assessment on their quality of life. Right, so this is a test for homogeneity. Lastly, this one was a little tough. Right, the context isn't terribly clear. Okay, so we have biologists wish to make pairs. It's so hard for me to read this thing. You look at this. There we go. There we go. Biologists wish to mate pairs of fruit flies having genetic makeups RRCC, indicating that each one has 1 dominant gene and 1 recessive gene for eye color, along with 1 dominant and 1 recessive gene for wing type. Each offspring will receive 1 gene for each of the 2 traits from each parent. To test our hypothesis about the distribution of traits among the offspring, biologists mate a random sample of pairs of fruit flies. So we have a single population and a single variable. And the variable is the distribution of traits. Right? We're checking the traits, and the traits can be like they get the 2 dominant genes and they get those 2 traits. You know, so we're kind of considering the 2 traits as a single variable for each fly. Right? And so this is a test for goodness of fit. Oops. Okay. So again, the thing we have to keep in mind is how was the data collected? How many populations was there and how many variables were there? Is there anything I can clarify on this set of examples? All right. So that brings us to the end of the activity. If you need more practice or want to review more things about this, please look at the resources in Canvas for section 11.1 and 11.2. There are practice problems, there's solution to those problems, there's study guides, all that fun stuff's in there. If you have any other questions or need help or support on anything from this class, please let me know. I'm happy to help. Just got to reach out and let me know. And besides that, we'll be starting with some new stuff next week. I'm trying to decide whether or not I'm doing chapter 12 or 3 next. I'll decide in the next couple days, and we'll get to that next week. Other than that, have a great rest of your day, and we will see you all next week.